His efforts push everyone to take positive steps to go where they ought to be. Thus, I feel privileged to invite Professor K.P. Hevagamage, the Director of UCSC, to welcome the gathering.
Thank you. I hope you can hear me. Am I correct?
Yes, we can hear you, sir.
Yes. Thank you. Very good morning to all of you. On behalf of the University of Colombo School of Computing and ICTer Organizing Committee, I warmly welcome all of you for the International Conference on Advances in ICT for Emerging Regions, ICTer 2020. Especially, I would like to welcome the Vice Chancellor of the University of Colombo, Senior Professor Chandrika and Vijay Ratna, the Deans and Directors of the University of Colombo, the Registrar and Bursar of the University of Colombo, keynote speakers of the conference, representatives of the industry sponsor LSEG Technology, and all invited participants of the conference, authors and paper presenters of this conference, academic, administrative, and other staff of the University of Colombo, and all other participants, including the students of the UCSC and other faculties and universities. First, I like to congratulate all authors and paper presenters for their acceptance of their submission, which were reviewed independently by domain experts in computing, both at the UCSC and other universities, including some experts outside Sri Lanka. Although we receive a large number of research papers, around 100 to 150, we seriously consider reviewers' comments when accepting papers. And therefore, collection of the papers contain both papers from the UCSC as well as the other universities. In this year also, we selected around 50% of the total number of submissions based on those review comments. I like to use this opportunity to say a few words about the ICTer conference and its history. ICTer conference was officially started in 2008, but it was based on the International Information Technology Conference, IITC, conference program which was established in 1998 by the late Professor V.K. Samaranayake. All of my colleagues at the UCSC contributed a lot for the IITC program, and it was a very interesting experience during the period 98 to 2007. I remember Professor Samaranayake wanted us to take this program forward while making it an international event. In 2005, we established IEEE Sri Lanka section, which helped with the help of all the academics in other universities. And later, IEEE Computer Society chapter was established in 2006. Main reason for the establishment of those local chapters to provide the international recognition for the research and development work carried out in Sri Lanka. In 2008, we renamed the IITC conference as an international conference in advances in ICT for emerging regions, while linking with the IEEE Computer Science Society. That is Institute of Electrical and Electronics Engineers Computer Science Society. As a result of that integration, all publication at the ICTer conference will be included in the IEEE digital library known as an Explorer. From 2008 to 2020, ICTer conference was organized in every year. And if you checked Google Scholar, you will see the conference has H-index 16 and I-index 31 based on the papers published at the conference. I must mention the two former directors of UCSC, Dr. Ruwan Veerasinghe, as well as late Professor G.N. Vikramanayake. They guided us to keep this conference moving forward as an international event at the University of Colombo. At the same time, the contribution of the academic staff and other universities was a big support for the success of the program during the last 12 years. Sometimes people ask the question, why do you want to organize a conference and start a journal since there are many conferences and journals today? Knowledge dissemination is a key responsibility of a higher education institute in addition to carrying out research and development work. It is one of the goals in the strategic plan of the UCSC, and ICTer conference is a one activity based on it. At the same time, UCSC wants to cooperate and collaborate with others, especially other academics in Sri Lanka as well as outside Sri Lanka, organizing this conference. Hence, we must acknowledge the contribution from the academic community outside the UCSC during the last 12 years for the success of the program, as well as IT industry in Sri Lanka who organize the conference as sponsors. It is not the same group who organize and contribute the ICTer conference. We usually appoint a new group after the conference for the next year. In this year, Dr. Sridharan and Dr. Kasun Karunanayake, who are the co-chairs of the conference, were given the challenge. Both senior and junior staff gave a big support to make it happen today. And also contribution from the universities, other universities, including IEEE Sri Lanka section and its members must be mentioned. I also like to thank this year industry sponsor of the conference, LSEG Technology, London Stock Exchange Group, PLC, a well-known IT company in Sri Lanka. The former venue of the conference was BMICH. We decided to change the venue when the new auditorium of the UCSC, Professor V.K. Samaranayake Auditorium, was established. Since the new auditorium was built considering some of the requirements of the ICTer conference, to use the technology for online participation, especially international participation. We were planning to have a blended form of a conference, first time in the ICTer history in this year. But due to the current situation, both in Sri Lanka as well as the other countries, we were forced to organize the conference as a fully online conference this year. So it's a very new experience to all of us. I personally think this is a very good opportunity to take things forward, considering the current pandemic situation as a challenge. I was told more than 350 people registered for the conference during the last few days, and there are more requests on the way. So hence we decided to webcast the program using the YouTube by converting ICTer as an open educational event for anyone in the world. With those remarks, it is my hope that everyone who joined the ICTer 2020 conference will take this great opportunity to enhance their knowledge and experience in computing. Once again, I would like to welcome and thank the Vice Chancellor and all other participants. Finally, I would like to wish all the participants of the conference a fruitful 2 days of lively deliberations in an online mode. Thank you very much and have a nice day.
Thank you very much, Professor. Vice Chancellor of University of Colombo, Senior Professor Chandrika Vijayaratne is an alumnus and an academic in reproductive medicine and endocrinology at the Department of Obstetrics and Gynecology in the Faculty of Medicine, University of Colombo. She's a senior professor since 2010. Professor Vijayaratna has an unfailing research record with multi-sector and international collaboration and outreach. She indeed is a prodigious leader, since her actions inspire others to dream more, learn more, do more, and become more. So, ladies and gentlemen, please welcome Senior Professor Chandrika Vijayaratna, the Vice Chancellor of University of Colombo.
Thank you very much. Can you hear me?
Yes, madam, we can hear you.
Thank you. Thank you, Dushani, for those very encouraging and humbling introduction. And our director, the indefatigable director, Professor Heva Gamage, and his very committed members of the academic and administrative staff, as well as the students of the UCSC. On behalf of the university, where I'm sure I'm joined by the rector, the deans, and the other directors, registrar, purser, librarian, as well as other groups of students and staff, I wish to congratulate you and convey our humblest greetings on behalf of the entire university community for holding this wonderful meeting despite many shortcomings, particularly in terms of Colombo being the red-colored high-risk center, for forging ahead with your 20th ICTer conference. And as our director said, despite the many drawbacks, I can say that even before this conference, from March 2020, the UCSC, the director and staff have been a huge tower of strength, not only to the University of Colombo, but to the entire system of universities by encouraging every one of us to go online and remain afloat in higher education, research, and scholarship. So in those terms, I wish to convey my greetings and many congratulations to all of you. And remember our visionary leader, particularly Professor Samaranayaka and the previous directors, for having kept a very long-term goal to be focused upon in terms of internationalization, globalization, and seeing the way forward in terms of ITC. And I must also convey my greetings to the industry, who have been a tower of strength, not only with conferences, but with provision of internships and arranging career paths along with the staff and students. In terms of this conference, what I saw when I perused at the topics yesterday, I was amazed at the diversity. I was amazed at the opportunities that can link ITC with the linguistic stream to neurology and medical diseases and understanding genetics, to a multitude of areas which our own university and the university community at large, both locally, regionally, and internationally, can join with. So all I can say is, as I have experienced, even particularly with the corona epidemic and the need to go online, your director has paved the way to take you further forward with precision, commitment, honesty, integrity, and above all, a high level of professionalism. And I'm sure the topics, the deliberations, the discussions, the networking that you all will have will prove to be even more productive than having a physical meeting, be it at the BMICH or even in our own university premises. So I'm sure you all will enjoy it. Please note that this knowledge creation, innovation, and dissemination, as our director said, is so important in your formulation of being a well-rounded graduate or postgraduate from the University of Colombo. So I wish you well, stay safe, and enjoy the next 48 hours. Thank you.
Thank you very much, Professor, for your valuable words. The co-chairs of ICTer 2020 are Dr. T. Sridharan and Dr. Kasun Karunanayake. Dr. Sridharan is Chancellor of his research interests are positive operators in ordered spaces. We will be hearing from Dr. Kasun about this year's ICTer conference. Dr. Kasun is a senior lecturer of University of Colombo School of Computing. He conducts research related to mixed reality, multisensory communication, and physical computing. He obtained his Bachelor of Honors in IT degree from University of Moratuwa in 2008 and his PhD in Electrical and Computer Engineering from the National University of Singapore in 2014. Dr. Kasun held the positions of Deputy Vice Director, Senior Research Fellow, and Research Engineer at Imagineering Institute of Malaysia and Interactive and Digital Media Institute at National University of Singapore. Research have been published in several international conferences and journals. So, ladies and gentlemen, please welcome Dr. Kasun Karunanayake, co-chairperson of
Thank you, Dushani. Hope you can hear me.
Yes, sir, we can hear you.
Thank you. Wish you a very good morning to you all. Thank you very much for being here in this moment. As the conference co-chairs, Dr. Sridharan and myself would like to welcome you all to the 20th International Conference on Advances in ICT for Emerging Regions conference, which will be held from today and tomorrow. So, due to the prevailing situation all over the world, for the first time, we have decided to conduct this conference completely as a virtual conference. ICTer 2020 is technically co-sponsored by IEEE Sri Lanka section and IEEE Computer Society. We are really thankful for the continuous support rendered by the IEEE Sri Lanka section. As in the previous years, all these presenting papers will be published in IEEE Explore Digital Library. Meanwhile, longer versions of some selected papers will be invited for the publication in ICTer journal. This year, we have received 142 submissions, but out of that, we have selected 127 submissions for reviewing, which belongs to 7 different tracks. All papers went through a double-blind review process, and each paper was reviewed at least 3 reviewers. We have compiled more than 400 reviews in total. Out of those 127 reviewed papers, 44 papers were selected as full papers. Full paper acceptance rate was 36.7. In addition to that, we have accepted 23 papers as poster papers, which seems to have a good potential to become successful research in future. Therefore, in combined total acceptance rate for both full papers and for poster papers are around 52%. This year's conference will feature 4 keynote talks by prominent academic personalities. Those keynotes will be delivered by Professor Ray Buntin from machine learning to deep learning, Professor N.D. Kodikara on deep learning to computer vision, Professor Adrian David Chiok on every sense, everywhere human communication, and Professor Aniruddha Joshi on designing technology for adoption by emergent users. As the conference co-chairs, we would like to take this opportunity to thank Madam Vice Chancellor, Professor Chandrika Wijeratne, for participating as our chief guest. And also, we would like to thank Professor K.P. Hewagamge, the director of UCSC, for his continuous support that he kindly offered throughout this year. We would also like to extend our sincere thanks to the publication committee headed by Senior Professor, Professor N.D. Kodikara, and all the track chairs of the publication committee, and all the reviewers for their commitment and dedication towards making this review process a success. Also, we would like to express our appreciation to ADMTC of UCSC for providing required technical assistance to organize ICTer conference as fully online conference. We would very much appreciate the conference co-secretaries, Ms. D.A. Sruvanmini and Ms. Sanduni Trimavitana, and all other conference organizing team members for their immense contribution given throughout this year. Finally, we would like to extend our gratitude to LSEG Technology for being the gold sponsor for this event. Regarding the conference participations, up to now, we have received 330 registered participants with Microsoft Teams as conference attendees. Meanwhile, there are several unregistered participants joined to this event through our YouTube streaming channel. Finally, we believe this conference would prove to be productive and memorable experience for all of you, where you could share with and gain from others the knowledge that would further enlighten the future computer research. Thank you very much. T. Sridharan and Kasan Karnanayake, Conference Co-Chairs, ICTer 2020.
Thank you very much, Dr. Kasan. Now we will be moving on to an interesting keynote which will be delivered by Professor Ray Buntin. Professor Ray is a professor in the Faculty of Information Technology at Monash University in Melbourne, Australia. He enjoys playing with text data and writing code. His research interests include theoretical and applied work in document and text analysis, machine learning, and probabilistic methods. So I would like to invite Professor Ray to deliver his keynote.
Okay, so I'm going to start by sharing my screen. Ooh, pardon me for, you're probably going to lose me. It's not. There we go. How's that? Is that? Have you got me on screen there?
Yes.
Yes,
Yes.
I can see your screen.
Good. Okay, so first off, thank you for inviting me to give this talk. I really do miss not being able to get out there and visit the university. I think getting to see different universities, especially since we have some very good PhD students coming from your university, would have been great to meet some of the IT faculty and spend a bit of time there. So just a thought for the day, just something, you know, don't forget to look after yourself in all these times. So what is this talk about? Machine learning, as it is happening now, it's really reached a ridiculous pace. There's so many teams, huge teams, doing all sorts of advances in industry. Publications are coming out so quickly that by the time it gets presented at the conference, sometimes it's already old news. I'd like to call this an academic singularity. The pace is just so fast, it's hard to keep up. But a lot of this is under the guise of deep learning, and I'd like to just go back a decade or two to when it was machine learning and talk a little bit about that. And this is really a big ideas talk. So just to remind us, Jeff Hinton had an article in the MIT Technology Review just appeared in my inbox this morning. AI pioneer Jeff Hinton, deep learning is going to be able to do everything. Wow, you can't say more than that, can you? But I think a lot of people are agreeing with him. So here's the outline of my talk. We'll look at some old school machine learning, bit of a comparison, then we'll look at some of the new ideas in deep learning, and I'll talk a bit about how that's changed things. So one concept we use a lot of, and this is in AI generally actually, is the notion of a hierarchical model. And this has been generalized to graphical models with the idea of knowledge graphs. And I use this in what's called a hierarchical Bayesian model, where you've got parameter sets, some parameters are parents of other parameters, and there's a sort of complex relationships in there. We also have common sense reasoning. Now, what do we see about this this figure? If you've been to America, you'd know this is a school bus. You look at this one tall gentleman there, probably a teacher. How do we know this? Common sense. So traditional AI systems didn't have this kind of common sense, and it was very difficult to figure out how to use it. But that is something we believe that's starting to emerge in deep learning. Knowledge-based reasoning. Well, I did refer to this a bit earlier, but you look up an encyclopedia and you've got a whole lot of facts. Knowledge-based reasoning is usually dealing with these sorts of facts. And it's the basis of what I was referring to earlier, knowledge graphs. And people are starting to embed these things in together. We have what's called a causal model. Now, I do want to point it out. So these arrows indicate cause. So what causes shortness of breath? Well, bronchitis or cancer. If you have cancer, what might it cause? Well, it will cause all of these things, shortness of breath. This is lung cancer is being implied here. Okay, so causal models are very good mechanistic models that help us understand our world. Here's a correlational model. We don't naturally get causal models from data. This is what we get from data, correlations. And let's consider diabetes in the middle there. And over in the far left, you'll see obesity. Well, we know they're correlated. Does one cause the other? For a long while, people thought obesity caused diabetes. We now know there's a common cause, which is called metabolic syndrome. Okay. So how do we use causality? Well, if you wanted to collect data about car accidents, what sort of variables would you choose? And this is how we used to do machine learning. We'd go in and we'd pick some variables, and we'd use causality to tell us which variables to get. Of these four here, quality of tires, that could cause a car accident. Color of the seats, no, probably not. External car color, maybe. If it's a black car, you might not see it at nighttime. So we pick variables based on a causal model. And that's how machine learning was put together, starting really in the mid-80s. But this then was a huge flaw of early machine learning. They didn't have the ability to create features from scratch. Nevertheless, causality is still a key thing we're working with. We can't learn it from passive observation, but what it does allow is better models. They're simpler and they're more stable. If you change your context, change your environment, change maybe the weather, our causal model still generally holds. Whereas typically models just built without causal understanding will be very fragile. So trying to build causal models is now in a sense, the holy grail of some current neural network work. I'm not going to say it's easy, but causal modeling is very related to probabilistic independence. That's about as far as I can go. There's some great reading here from Judah Pearl. Hyperparameter tuning. Oh, sorry, my clock. There it is. So this is, again, I think this is another success story of the early machine learning work. We'd have a machine learning algorithm, And then we tune the parameters to get it work better. And it was the Gaussian processors that were really very good at these. What these are, a Gaussian process, is an amazing low-dimensional function fitting method. Works brilliantly in low dimensions, but because it only works in low dimensions, we can use it for tuning a few parameters, but we can't use it in general tasks for machine learning in many cases. Vision, natural language processing, it doesn't deal with it, but it's great for parameter tuning. This is a bit aside. Information retrieval, what's that got to do with machine learning? Well, you know, here's the idea. You put in a query and you get some answers. But it turns out, I always wondered what information retrieval was. I never had a good understanding from an AI view, a semantic view. Information retrieval is machine learning. So you get one example and you say, here's my one example. I'm going to learn for it, and then I'm going to retrieve a whole bunch of similar things. So it's called one-shot learning in the deep neural network community. And this idea was sort of developed independently by a number of groups. The IR people started coming up with this about 3-4 years ago. The deep neural network people, in particular the image people, created the concept of one-shot learning. But now it's gone mainstream. So Google is starting to install some of the machine learning techniques into their system. Active learning. I think this is one of our big achievements, actually. And just to show you the details there, we've got way too many unlabeled images. Sorry. Yeah. Oh, it's gone anyway. So we've got way too many unlabeled images. Generally, what we can't get is labeled images. That's the big problem in machine learning. We never have enough labeled data. In typical medical problems, you may have 300 or 400 patients with this particular unusual disease in your registry. So you can't learn from large numbers of cases. But sometimes, say in image work, we have huge numbers of data. We just don't have the labeled data. How do we get the labeled data? So that's what we'd like. This is what we want to generate our models, to do our machine learning. So this is how we do it. We're going to select a subset of the labeled data and give it up to some annotators. Mechanical Turk is a good example. And we'll pay them to label the data for us. And that way, with a bit of money, we can get some labeled data generated out of the unlabeled data. But which cases are we going to give the users? It turns out if we do it carefully, and that's what active learning does, it carefully selects which data we're going to show our annotators. We can save ourselves about 3 times the amount of data and more sometimes. All right, so active learning. Finally, almost Bayesian theory. I use this as a basis for, here we go, developing new methods and coming up with alternative interpretations. So for me, it's the glue. It's the theory that helps me put interesting bits of machine learning together. Absolutely critical. And I'm not really illustrating this in this talk, but just pointing it out. Now, the final thing, metrics and divergences. This is about the only math I've got here, I think. So the first formula, we've got an empirical data distribution. Now, in our learning, what we do is we set up a cost function, we optimize a cost function, and we're going to fit the parameters of our model. And that's represented here. And here is our data, and here's our model. The idea is we want the data to be a good fit to the model. And that fit can be done in different ways. And there's a whole theory of this. Metrics and divergences. The basic term the basic theory is proper scoring rules, which the statisticians talk about. And the final bit of the theory is we sometimes add smoothing terms, and this is called regularization. So see there, I've added a second term into my cost function, and that term is to encourage simpler models, and some people relate it to the famous Occam's razor. So there's a lot of theory in this metrics and divergences. I listed the 3 big theories that our theoreticians work with. They've got tables like this. My golly, which cost function am I going to use? What a choice. I'd call this an embarrassment of riches, but there's very good guidance in this in certain things you do. And the most commonly used one is Kullback-Leibler divergence, which is actually a maximum likelihood approach. Okay, so that's my old school machine learning. What have we learned here? What have we got? First off, we can build models. I haven't illustrated this, but we've got our different kinds of models. In particular, the neural networks came out of this model building approach, decision trees and so have you. The basic theory that almost all our early machine learning worked with was linear modeling, and then we really hit a wall. We could extend things a bit, and if you go into the more esoteric bits of machine learning, you'll see these 2 terms mentioned, kernels and non-parametrics. But all they did was extend our linear models a little bit more. But then we've got these cost functions, which I've been telling you about. And of this, it's our models and our cost functions which have moved into deep learning and are being used in the deep learning world. Now, the other thing, which is kind of interesting, we developed all of these learning paradigms, active learning, transfer learning, online learning, a whole bunch of unsupervised learning, but not all of them we could get working. We couldn't really get transfer learning working that well. Some of these paradigms evaded us because we didn't have the right technology. And learning was a difficult craft, and along came deep learning. And what deep learning allows us to do is it just makes machine learning a lot easier. So the first thing is, you've got these black box methods. What do? You define a model, you specify a cost function, and the black box does everything for you. Whether that be TensorFlow or PyTorch or one of these systems people are using. And I like to think of this as machine learning without statistics. So the basic idea was, instead of my PhD students spending a year doing complex statistics before they could even begin to start doing their PhD, they could begin within a month. They just have to learn a bit of PyTorch, learn some principles, and away they went. So we've basically cut out a lot of complex statistics out of our machine learning and liberated a lot of people in what they can do. The next, and this is equally important, the next bit of brilliance is the team then, they take these models and everything and they port it down to a GPU. Now, I had students working with me in the like 2011 who were doing CUDA programming. You know, it was a horrible language. It's a weird version of C. Now you don't have to do this. It's all done for you, and basically you write Python. Amazing. But everything's ported down from your Python specifications down onto a GPU and run for you. Another thing, which is, I'll sort of cover a bit later on, but deep learning lets you learn representation. Now, remember I said earlier, we'd use our causal model of the world to figure out what variables to include in our algorithm. Now, that's all good and well if it's a moderately simple problem, but what if it's just images? Recognize a cat. And all you've got is a raw image, pixels. How do you recognize a cat? What are your features? God, I don't know. But deep learning generates the features. So I've highlighted there learning representations. That's really the key thing it does. And that's actually the name of the ICLR conference, International Conference on Learning Representations. That's the biggest conference on deep learning. Finally, these models have what we call a huge capacity, loads and loads of free parameters, and lets them build really complex models so they can do complex things like natural language translation. And the way I like to think of this, you put it all together, and what do you get? Modeling in the large. No longer do you spend all your time fiddling about with arcane details, little bits and pieces of statistics, and complex aspects of, say, Markov chain Monte Carlo samplers. Instead, you're modeling in the large. You're putting together architectures. It's almost a godlike capability. So, and this, I think, this cartoon captures it beautifully. The old versus the new. And this I got from a Stanford NLP course taught this year. At the top side, we've got an old-style machine learning person, and they're apologising because things aren't working quite well. And as you can see, they're outputting a whole lot of complex mathematical jargon. I'm not going to read it out. Down the bottom is our deep learning person. They've probably just come off the ski field, still have their crazy hat on. Oh, it's easy. Just stack more layers. It'll work. You know, that's the difference between my earlier PhD students and my later PhD students. So let's look at how some of these things have, and now what we're doing in deep learning and consider the differences. So here's a single layer neural network. It can't do much. All it can do is give you a straight line, really. As you get more layers, it gets more complex. And this, by the way, it's a great tool. You can get the slides and play with this, tensorflow.org. Even once you get to 5 layers, you get to pretty complex models. And what this means is, and this is how we like to think of it, in deep learning, we're learning different levels of representation. And let's suppose all the images we're looking at are faces. Well, at the lower level, we've got bits and pieces of things. At the middle level, we've got facial features. And at the upper level, we're recognizing different kinds of faces, maybe men versus women, children, different things. Now, all of this is driven, by the way, by convolutions. So the whole recognizer is repeated all over the image. But this is the representation learning that deep learning is doing. And this is what we could never do in our older methods. And this is what people are then can achieve with these new systems. They can build up complex models using architectures. And what we have here is we're building up a scene recognizer that's going to describe what it sees in front of it. There'll be some feature recognition. There'll be some words coming in, maybe from the text. Hello?
Knowledge-based reasoning. Well, I did refer to this a bit earlier, but you look up an encyclopedia. Knowledge-based reasoning is usually dealing with these sorts of facts. And
oh, you mean I'm not actually trying to present the knowledge-based reasoning aspect here. All I'm trying to do is, in fact, I could have tossed out the semantic part. What I'm trying to do is show you here is where they've put together different parts of deep neural networks to build a more complex system. So they're blocking together modules, and these would have been generated with Python to build a complex recognizer. And in fact, they may be plugging into a knowledge base, which some people are starting to do, and doing traditional knowledge-based reasoning to run that and support it. So, but the main aspect here was trying to show you the blocks of system and the way you could build this up as an architecture, looking at it as a large system. Okay, architecture, augmentation, the next idea. So on the left, we've got one image. We can generate a whole bunch of other images, and maybe knowledge tells us that those images are also valid. So we can rotate the image. We've still got a valid butterfly. We can change the colors. We've still got a valid butterfly. It may not be a valid species of butterfly. So data augmentation means we're going to generate new data out of data we have based on digits. So the US Postal Service used to have an annual zip code recognition competition, and one group one year did incredibly well by doing this trick. They took the data that they were given, and then they basically added the ability to rotate, shift a bit up and down, and that dramatically improved their recognizer because they were effectively having 10 times as much data. Now, but the issue is that trying to put this knowledge about rotation or shift into your classification algorithm is actually going to rotate, shift a bit up and down, and that dramatically improved their recognizer because they were effectively having 10 times as much data. Now, but the issue is that trying to put this knowledge about rotation or shift into your classification algorithm is actually very hard. And so what the data augmentation people do is they generate new image instances from the old image instances. And they're starting to do it in text as well. So it's going to generate a number of new images to use in training, meaning you've got more data and meaning you're going to learn faster. This has a probabilistic interpretation, rather like a convolution. You can add a theory around this so that you can integrate it into your algorithms, and it all works very well. Another idea, and this is another idea that we've actually been doing for a long while in regular machine learning, but not very well, because we didn't have the machinery to put it together. So you've got three different tasks here, classification tasks, A, B, and C. Maybe recognize a truck, recognize a tank, recognize a bus. Well, what you can do is they could share their low-level features. And only the upper part of the network are made different. Now, this feature sharing means you can, when you add a new task, if you add C as a new bootstrap